Hi, everyone. This is Scientific Sense Podcast. My name is Gill Eapen. My guest today is Dr. Paul Sutter, who is a research professor at the Institute for Advanced Computational Science at Stony Brook University and a guest researcher at the Center for Computational Astrophysics with the Flatiron Institute. He is also the host of a popular podcast, As the Spaceman. Welcome, Paul.
Oh, thank you so much for having me.
Yeah, thanks for doing this. So I'm a big fan of your podcast, and I have no background in astrophysics, but I learned a lot of stuff from your podcast. And you sent me a paper. I haven't read through them. I just got them from you. But it's a very interesting topic. It's about cosmic voids. You say here, cosmic voids are emerging as the novel probe of both cosmology and astrophysics, as well as fascinating objects of study themselves. So before we get the details of the tools that are being used here, what exactly are cosmic voids?
That's a wonderful question. Cosmic voids are the largest empty regions in the universe when we zoom out to the very largest scales in the cosmos. We're talking scales where galaxies appear as just single points of light, where all the hundreds of billions of stars and thousands of light years that comprise a galaxy is just a tiny little dot of light. A pattern emerges in this distribution of galaxies, where galaxies aren't scattered around randomly, but instead they form a pattern, they form a structure, and we have a name for this structure. We call it the cosmic web. And this cosmic web is made of long, thin filaments, like highways of galaxies, and dense clusters, which are like cities of galaxies, and broad walls and sheets in this intricate and beautiful three-dimensional structure. But the cosmic web itself, even though it contains almost all the galaxies in the universe, doesn't take up a lot of volume. These clusters are very dense. The filaments are very thin. And so the vast majority of the volume of the universe is actually relatively empty space. And we call these empty spaces the cosmic voids.
So is there a sort of a physics reason? So going back to the Big Bang and the expansion of the universe, is there a sort of a physics reason why they should exist, or is there a reason they should not exist?
Oh, yeah. When we first discovered the large scale structure of the universe, the first hints of this came in the 1950s and 60s. And then in the late 1970s, early 1980s, our cosmological surveys became sophisticated enough that we could finally pick out this structure. And at first, it was a surprise. We had assumed that galaxies would just be scattered around randomly. We had already known about clusters of galaxies, so we just thought randomly galaxies clump up together due to their mutual gravitational attraction, and that would be it. But once we discovered this cosmic web, we had to explain it. And there have been many attempts to explain it, and we do have an understanding of where the cosmic web comes from. And of all places, it comes from the very earliest moments of the universe itself, when our universe was less than a second old. There were random fluctuations. And when our universe was less than a second old, it was smaller than the volume of an atom. It had a temperature of over a quadrillion degrees. It was an extremely exotic place, but it was still a place where we can understand with our theories of physics. And we worked out that in the earliest moments of the universe, there were random fluctuations, just random tiny pockets of density difference. We're talking less than 1 part in a billion density difference. Totally random. And then as the universe ages, as it evolves, as it gets bigger, as it expands, as it cools off, something happens to these tiny density differences. Places with slightly more density than average, or just a little bit more clumping than stuff, even 1 part in a billion, have a little bit stronger gravitational attraction. And so they pull on their surrounding matter. And then as they pull on their surrounding matter, they get bigger They get even more dense, they get larger, which gives them an even stronger gravitational pull, which causes them to pull on even more stuff around them. And this process builds and builds over hundreds of millions of years, eventually leading to the formation of the first stars, the first galaxies, and then the emergence of the cosmic web. So what we see today as the cosmic web, this structure, this pattern that fills up the entire observable universe, the very largest pattern found in nature, including the cosmic voids, was founded in the earliest moments of the Big Bang itself. And so what we understand as the voids are the leftovers. If you're going to build these massive structures like galaxies and filaments and clusters, you have to take that material from somewhere. It's like a cosmic quarry. If you're going to build a giant statue, you have to go somewhere else and dig stuff out of the ground in order to build that statue. And so that becomes the voids. These supply the material to build the large structures in our universe.
And so if I understand this correctly, Paul, so gravity has sort of a reinforcing effect. So the initial conditions are you have some random dense areas. It has more gravity than other areas. It starts to attract more, and it gets more material, and it's attracting material from other places, and those things become more and more void, so to speak, and less gravity and start to lose matter. So this is sort of a winner takes all phenomenon in the universe, and voids happen because of that. And so the paper is about how to identify, how to examine these voids, right? So you have a toolkit here, VIDE, the Void Identification and Examination Toolkit, which is an open source Python C++ code for finding cosmic voids in galaxy redshift surveys and others. So this is the general trend, right? I don't know much about what's happening in astrophysics, but I would imagine machine learning and a lot of the programming techniques that are happening in other industries are now really making a difference in astrophysics as well, right? Is this a phenomenon?
Yes, so the toolkit you mentioned, VIDE, that is vide, that is the French word for empty. That's how we got the name. When we developed this toolkit, I was based at the Paris Institute of Astrophysics, and so it felt very appropriate to name it after a French word. And this is a generalized toolkit that our research team has developed for finding and identifying voids, because it's not a trivial task. If you take a survey, if you map the universe, you collect all the galaxies and the locations of those galaxies, and then it's not necessarily easy or well defined. Yeah, visually you can pick out the voids. They're just the places with not a lot of galaxies. But to mathematically define that in a way that you can use to understand the growth and evolution of the universe is a much trickier enterprise. And that is what we have encapsulated in our software tools. And we have since used this toolkit, and many researchers from around the world have used this toolkit to identify identify voids in simulations of the universe, identify voids in the real universe, find ways to use voids to understand the growth and history of our universe, use voids to find ways to understand the nature of dark matter and dark energy, which are massive mysteries in modern cosmology. And you mentioned machine learning, artificial intelligence. It's actually the progression of the use of AI is actually the other way around. Machine learning, artificial intelligence has been used in academic research for decades, and only now it's becoming more mainstream on the commercial side. I personally don't employ machine learning or artificial intelligence in my research, but I do collaborate with others who do, and they have been investigating this, using this, trying to use sophisticated neural networks, machine learning, etc., tools to help accelerate and enhance scientific discovery. And in fact, very recently, we've discovered through machine learning just how much information is available in the voids. So, for example, when we go out to perform a galaxy survey and we build a massive telescope and we scan the heavens and we map, thousands, hundreds of thousands, millions of galaxies, which represents, by the way, less than 1% of the volume of the universe, but that's what we got going for us. When we do this, we try to take the properties of these galaxies, their sizes, their shapes, how they're arranged, the structure they form on the cosmic web, and try to connect it to fundamental physics. We try to connect it to the fundamental nature of gravity, to the constituents and components of the universe, like dark matter and dark energy, and how these interact with normal matter. And traditional cosmology relies on a relatively limited set of tools, of statistical measures, of properties that we can use to connect to the things we care about. With machine learning, we are opening that up. We are broadening those tools that we can use. So we're not limited to simple statistics, things that we can run with a simple analysis algorithm. One of the great benefits of machine learning and neural networks in particular, when it comes to this problem domain, is that it is neural networks are very, very good at finding deep and hidden connections in the data. And we are using that to discover, to mine these galaxy surveys to get as much information out of them as possible. But we have to calibrate these results on simulations. We have to train our algorithms, we have to train our neural networks, and we train them on simulated universes, mock universes. And when we do this, we have recently discovered that most of the information content of the universe is not actually in galaxies. They're not in the galaxy positions, their sizes, their shapes, their colors, their arrangement. Instead, we have learned through our investigation of machine learning and cosmology that the voids contain most of the information in the universe.
That's a bit counterintuitive for me, Paul. So what do you mean the voids contain most of the information? What type of information are we talking about?
Oh, it's absolutely counterintuitive, and it's one of these juicy results that people who have been working on voids for a long time have suspected but never been able to prove or demonstrate. And now we have this solid piece of evidence that, yes, we've been right all along. And the issue is our universe is very old. It's about 13.8 billion years old. And it started out very, very simple. It started out as a hot, small ball of plasma with an extremely high temperature. And this cosmological, the state of this universe was driven by very fundamental parameters. There are very fundamental physics, like the force of gravity, like the strength of gravity, like the amount of dark matter in the universe, the properties of dark matter in the universe, the strength of dark energy. There are these very, very simple, straightforward laws and properties of the universe that governed its early evolution. But then you fast forward 13.77 billion years, and you don't get to observe directly that raw physics that you're after. We can't directly observe, say, the force of gravity. We can't directly observe the amount of dark matter in the universe. All we have are observations of galaxies and their colors and their sizes and their shapes and their positions. They have these statistical properties of the galaxies. That's what we have to go with. And we have to observe these galaxies in order to peek into the unseen, to peek into the nature of dark matter and dark energy and the nature of gravity. But galaxies are really, really messy places. They're complicated
It's also a small
places.
part. Yeah, as you say, it's also a small part.
Yeah, exactly. They only capture a small part of the volume of the universe. And They are extremely complicated places. Stars live and die. Supernova go off. Black holes form and eject winds that heat up the galaxy. Sometimes they merge together. Galaxies are incredibly complicated places, and they're so complicated that inside of galaxies, they mask the original state of the universe. They mask the fundamental physics of cosmology, sitting between us as observers and scientists and the pure cosmological data that we're after, the nature of the fundamental components of the universe. Sitting between us and that is a whole bunch of very messy, very complicated astrophysics. Now, many astrophysicists are just interested in those astrophysics and they make a living studying that. But as cosmologists, we're trying to go through that. The benefit of the voids is that they are not complicated.
Yeah.
We've been able to demonstrate that they have barely evolved in 13.8 billion years. The voids are time capsules because they don't have galaxies. They don't have stars. They don't have weird, complicated astrophysics. They don't have magnetic fields or cosmic rays or neutrinos or whatever. They don't have any.
They won't even have dark matter, right? Because again, dark matter is affected by gravity. So it's really truly a void.
Yes, in the deepest cores of the voids, they are truly void of all matter, even dark matter. As you go away from the centers of the voids and start to approach the cosmic web, you do start to see more dark matter there. And then at the very edges of the voids, which is the cosmic web, you see a lot of dark matter along with a lot of normal matter. And, you know, there's like hydrogen atoms floating around here and there. There's radiation pouring through. There might be a small dim galaxy sprinkled here and there, but the deep cores of the voids are truly devoid of matter. And this makes them exceedingly simple.
Yeah.
They are relatively unevolved. These are like fossils into that give us a glimpse of a universe as it was billions of years ago, a pristine, a time capsule. And this is why they capture more information than the galaxies do, because the galaxies are small and super complicated.
Yeah, so if you're after the structure of the universe and the evolution of that structure, cosmology more generally, then as you say that the voids provide you more information for multiple reasons. One is it's a big part of the universe, so we can really ignore it and understand the universe. And the other is, as you say, it hasn't really changed much. So it has sort of a better playground to understand the structure. Am I thinking about it the correct way?
Yes, that's exactly right. Because they are more pure, because they are more pristine, they give us a better window into the fundamental structure of the universe. And from there, it gives us a better window into the fundamental physics of cosmology that we're interested in.
And so this tool again, so what is the data that goes into it? What's the process that you use?
Yeah, the inputs in our particular tool in VEED are galaxies. And really, because this is cosmology, because we're looking at the very largest structures in the universe, we don't care about the properties of the galaxies themselves. We're compressing all of this. If you imagine the Milky Way galaxy, which is 100,000 light years across, contains hundreds of billions of stars, is a complex, dense, evolving environment. There are up to 2 trillion galaxies like the Milky Way scattered throughout the universe. And when we want to go looking for voids, all we need to know is where that galaxy is. That's it. 3 pieces of information, just its coordinates in the universe. That's it. That's all we care about. That's all we ingest is a set of points, of positions that represent or trace the distribution of matter in the universe, that trace the cosmic web. And from there, our toolkit goes. It starts running.
Yeah, so you mentioned dark energy too. So I'm wondering, Paul, does this have some implications for dark energy? I mean, the other puzzle in physics, this accelerated expansion that could potentially ultimately result in some sort of a big rip of the space-time fabric. Are the voids playing a part in it?
Oh, that is an excellent question. And in fact, yeah, so dark energy is an extremely mysterious component of our universe. We do not understand dark energy. Dark energy is a name we give to the accelerated expansion of the universe. So the universe is getting bigger and bigger every day. We've known that ever since the time of Hubble 100 years ago. But about 20, 25 years ago, we learned that the universe is getting bigger and bigger, faster and faster every day, and we do not understand why. Whatever is driving this accelerated expansion is a form of energy. It's a form of anti-gravity, and it takes up roughly 2/3 of the entire energy budget of the universe. Most of our universe is made of this mysterious form of energy that we do not fully understand. In the universe, we believe, we're not sure about this, but we strongly suspect that dark energy is a property of space-time itself. It's a property of the vacuum. That if you take a box and empty out all the particles, all the radiation, and you have a perfectly empty box, there is something in there. There's an energy associated with the vacuum of space-time itself. We call this quantum energy. We believe that dark energy is a manifestation of this quantum energy. So when you look out at the wider universe and you start asking, where's the dark energy? Well, yes, technically there's dark energy in the room I'm sitting in right now. But there's also tons of normal energy. There's stuff, there's me, there's my desk, there's some light flowing in, there's the rooms of my house, there's all this stuff, and all this stuff has so much more mass, so much more energy than dark energy. It completely overwhelms it. The same is true in a galaxy. You look inside of a galaxy, yes, there's dark energy in a galaxy, but there's so much stuff in a galaxy, it completely overwhelms the dark energy. But you look inside a void, there's nothing there. Voids are actually filled with dark energy. Voids are actually not just passively emptying themselves out to fuel the construction of the cosmic web. They're actively pushing on the edges, and they're doing that because they are filled with dark energy. They are filled with this anti-gravity. The accelerated expansion of the universe is actually being driven by the voids, by the cosmic voids. That's where it's happening. It's not happening here in the Milky Way. It's happening in the cosmic voids. So this is another advantage of cosmic voids. If we want to study dark energy, we have to go to where it is, and it's where nothing else is, and that is the voids. As to the future of the universe, as far as we can tell, there is some uncertainty, or a significant amount of uncertainty on this statement. The universe is not apparent. It doesn't look like the universe is going to die from a big rip. A big rip is a scenario where the accelerated expansion goes out of control and doesn't just drive galaxies away from each other, but rips apart galaxies themselves, rips apart solar systems, rips apart planets, rips apart atoms, where everything gets torn apart due to this out of control dark energy. It doesn't seem like dark energy is that strong. It seems like it is strong enough to eventually tear apart the cosmic web, which it will in about 10 to 20 billion years, but not strong enough to overwhelm the gravitational bonds already in place. So the Milky Way isn't going to get torn apart by dark energy. I do have to say, there is uncertainty on that. That is why we are continuing in our galaxy surveys. That's why we are continually refining our techniques, and that's so that we can get a better measurement of the properties of dark energy.
So do you have any measurements, or do you have any intuition or a hypothesis as to sort of the distribution of dark energy inside a void? What I'm thinking is that, is dark energy stronger as you get closer to the center or something like that?
Yeah, this is something we don't fully understand, honestly, because we don't know what dark energy is. We're just guessing at what its properties might be. So it's this unknown entity in our universe, and we are currently taking bets, taking guesses as to what it could be. And right now we're working in the stage where we are making guesses about its properties, then going to try to measure those properties. And then if we can validate the properties, then we can go out and turn back to our chalkboards and try to develop a theory of what it is. I'll give you an example. The simplest model of dark energy is something called a cosmological constant, where dark energy is absolutely perfectly uniform throughout the entire universe. So if I draw a particular volume around me right now, there is a certain amount of dark energy in that volume. It's very, very weak compared to all the stuff, so I don't need to worry about it. If I take this same volume and move it to the center of a void, all I see is dark energy because there's nothing else in that volume, but it's the same amount of dark energy as is sitting in this room. It's completely constant in the universe. And it's completely constant in time. That dark energy doesn't change in time. The amount of dark energy available that was existing in the universe billions of years ago is the same as today. But billions of years ago, the universe was smaller, it was hotter, it was denser. And so all the energy from all the normal matter was able to overwhelm it. Nowadays, the universe is big enough, cold enough, the voids are empty enough that dark energy can start to flex its muscles. There are other ideas of what dark energy could be. Some theories to explain the existence of dark energy say that dark energy changes with time, that it was weaker in the past and now it's getting stronger, or maybe it goes up and down with time. There are ideas that dark energy does cluster, that it does collect into regions of more dark energy and less dark energy. Maybe that clustering is associated with the cosmic web. So you go into the densest parts of the cosmic web and you're going to find more dark energy there. Or maybe it's the reverse. Maybe what you said is correct. You go into the deepest hearts of the voids, and that's where you find the most dark energy. At this stage, we really don't know.
So if you look across clusters of galaxies or galaxies themselves, do we see differences in dark matter and dark energy? I mean, we can probably have deduced this from motions, right? Do we see a difference in different galaxies?
Yeah, so dark matter is yet another cosmic mystery. So dark energy takes up about 2/3 of the energy budget of the universe. Dark matter takes up about 1/4 of the energy budget of the universe, and that leaves around 5% for everything that we know and love. Every single element on the periodic table, every single star, every single hydrogen atom in the universe. Everything we understand about physics makes up less than 5% of the entire cosmos. So we've got our work cut out for us. Dark matter, we arrived at the existence of dark matter through completely different observations. We arrived at the existence through basically weighing galaxies and developing different techniques for estimating the mass of galaxies. And every technique we can devise tells us that there's more matter in a galaxy than what can be seen, than what is emitting light. And so we have arrived at a hypothesis called dark matter, where we believe that dark matter is some new kind of particle, some fundamental particle that we have not encountered in particle physics in our experiments before. This particle does not interact with light. It may not even interact with itself, but it is matter, and it does have mass, and it does clump up. So when we look at the cosmic web and we look at this vast arrangement of galaxies with filaments and clusters and walls, these galaxies are like lighthouses on a distant shore. They are tracing the underlying dark matter for us. That if you could put on special glasses that let you see dark matter at the very largest scales, you would also see this cosmic web. And where there's a lot of dark matter, you see a lot of galaxies. Every single galaxy, we believe, is surrounded by a dense halo of dark matter that it is embedded inside. Every cluster, every filament, these are all shaped by dark matter. And this is why the voids really are empty. They're not just empty of normal matter, they're also empty of dark matter.
And so going back to the voids and dark energy again. So if I understand this correctly, Paul, the larger the void, the more dark energy, right? So if I'm thinking about it correctly, if I think about the universe as sort of a flat surface, and I have this big patches of black things in it, which is voids, that is full of dark energy, let's say. I would expect the bigger dark thing to expand faster, right? Because it has more energy. If that's the case, then going back to all the data that we might have now, could we sort of predict what the situation would be in the future?
Oh, absolutely. So we have very sophisticated computational models of the universe where we take the fundamental physics of the universe. We understand, or we believe we understand, the nature of gravity, the nature of electromagnetism. We can plug in the mysterious parts that we don't understand, like, okay, we don't know what dark matter is, but we know its properties. We know it doesn't interact with normal matter, but it just self-gravitates. We can plug in the properties of dark energy. You can assume, okay, it's just a cosmological constant, and it just sits throughout the background of the universe, and it affects the overall expansion rate of the universe. And we can simulate, and we can, to a large degree, faithfully recover the actual observed universe that we see in our data. So we know we're on the right track. And yes, we can evolve these simulations past the present day. We can do like climate or weather forecasting, but instead of looking at next week's weather or next century's climate, we're looking at the next 20 billion years of cosmic evolution. And when we do that, which is very speculative, because again, this involves physics or aspects of physics that we do not fully understand, when we do that, we see the dissolving of the cosmic web. The cosmic web actually stopped building itself around 5 billion years ago when dark energy came into prominence, when our universe expanded and diluted enough that dark energy became the dominant player. And so, yes, we have a cosmic web today, but this cosmic web is not going to last forever. Some galaxies are still merging together. Some processes of formation are still happening, but that formation is slowing down, and eventually it will stop and reverse and tear apart.
But in some sense, we back computed dark matter and dark energy, right? So there is still a possibility of new physics as well, right? Where do you stand on that?
Oh, it's not just a possibility of new physics, it's a necessity of new physics. We do not understand dark matter and dark energy. We do not know the identity of the dark matter particle. We have not identified it yet. This is an active research program. This is something we're trying to figure out. We know the properties, we know how it behaves in the universe, but we don't know what's causing it. And the same for dark energy. We observe an accelerated expansion of the universe in the present epoch. We do not know how strong dark energy is. We do not know if it is getting weaker or stronger with time. We do not know if it is clumping together. And most importantly, we don't understand what is creating these properties. We have a lot of ideas, but we don't know if they're right or not. A solution to dark matter and or dark energy will by necessity involve new physics, physics beyond the standard model, physics beyond what we currently understand, which is one of the reasons why it's such an exciting research program. Because it's not just about going out into the universe and measuring some property and getting better at measuring that property and then calling it a day. It's about using these measurements to accelerate discovery itself, to enable new breakthroughs and new knowledge in physics.
And understand, Paul, on top of that, we have this Hubble tension, as they call it. So different techniques that we use, early techniques, late techniques, they all seem to yield different Hubble constants. Wendy Friedman has been on the show talking about it some time ago. Um, so where are we on that? Are we getting closer to the number?
Yeah, no, it's such an interesting dynamic happening now in cosmology where we try to estimate some very, very fundamental numbers because the fundamental numbers tell us they connect to our theories, our fundamental knowledge of physics. One of these numbers is the present day expansion rate of the universe. And we've gotten very, very good at measuring this number. But we have different sets of probes. We have different ways because we're scientists. We're never just going to use one way and call it a day. We're going to use different methods to come at the same result and see if these cross-check with each other. And there are sets of measurements that use the local universe, that use local measurements, relatively nearby techniques. They get one set of numbers, and then we have a completely different approach that uses very distant objects, very, very far away things, that gives a different set of numbers. And these numbers are not very, very far apart. They're only different by like 0.5% or something. It's something very, very small. But we're so precise in these measurements that that is big enough to matter. There are several potential resolutions to this conflict that has been dubbed the crisis in cosmology. I think that that name is a little bit overwrought, but I'm not in charge of naming. One solution is that we need new physics. Like, okay, maybe this is telling us something important about the universe. Maybe dark energy does like mess around in the early universe when we thought it didn't play a big role, and it turns out it does play a big role. Maybe there's something else going on that we haven't thought of yet. Maybe we need to revise our understanding of gravity or something like that. It can also be a measurement issue. These measurements are not easy. They're not necessarily straightforward. They come with a lot of work to go from measuring the positions of supernova or galaxies in the local universe and turning that into an expansion rate is actually an extremely difficult process. And a process that, if there's like a little calibration error or a little thing we're misunderstanding about the physics of the galaxies themselves, like I said, galaxies are very messy places. If we're getting something wrong there, it's possible to make this problem go away. And so it's not exactly clear yet if this is a measurement error or something fundamental that the universe is telling us.
Yeah, so I know you have to go, Paul, so I'll finish up with this. So in my non-astrophysicist brain, I'm thinking, Paul, if universe is like making a soup, tomato soup, let's say, the initial conditions matter a lot, right? How much water I put in there, how many tomatoes I have in there and all of that. And so since we have only one observation of this soup making process, those initial conditions ultimately get us here, how fast it's cooling and all of that, right? So so is it true that what we are seeing is sort of a random tomato soup making process that may have a lot of noise in it?
Oh, absolutely. And we even have a name for this. We call it cosmic variance. There is no theory of physics that can tell us where the Milky Way will appear in the universe. We are located in this part of the universe with these neighbors. There's that cluster over there. We're in this branch of a supercluster. The cosmic web looks like this around us. There's no theory of physics that predicts that precise arrangement of the cosmic web, of the locations of galaxies. Instead, the theories of physics predict the statistical properties of the cosmic web. It won't say you're going to find a small galaxy over here, a medium galaxy right here, and a large galaxy right here. But the physics of the universe, what we understand it, will say, okay, if you look in a large enough volume, on average, you're going to see 10 small galaxies, 14 medium galaxies, and 3 large galaxies. And their average separations will be like this, and their average colors will be like this. We can predict the statistical properties, the on average properties. This is not perfect, as you might imagine, because we only have one universe. to observe, like you said. And so this does limit, it fundamentally limits the amount of information we can gather from the universe. We are nowhere near that limit because we have mapped less than 1% of the volume of the universe. So I suspect we have a lot more to learn until we hit that cosmic variance limit.
So finally, Paul, so what excites you the most as you look forward, let's say 10, 15, 20 years? What would be the observation, some sort of theoretical advancement, or the combination of those would be the most exciting for you?
I'm most excited by the surprises in science. I'm not super excited by the planned, programmed studies where we're going to do what we did 10 years ago, but slightly more sophisticated. I want surprises. I want novel ideas. The discovery of dark energy itself was a complete surprise. The discovery of dark matter was a complete surprise. I think we need more surprises. I think we need to enable more surprises. I think we need to give crazy ideas a chance, crazy research programs a chance, crazy observational programs a chance. And I think we need to let the universe surprise us and delight us. And I think that's how we're going to crack mysteries like dark matter and dark energy, by being willing to be surprised.
Excellent. Excellent, Paul. Thanks so much for spending time with me. Really enjoyed it.
Absolutely. Thank you for having me.
Thank you.